Year 13, Year 1 Further Maths, Sequences in Series, Lesson 4, Proof by Induction, with a focus on recurrence relations. So here's a refresher of the stages of proof by induction. Prove that the result is true for a starting value, often but not always n equals 1. Assume that the result is true for some integer n equals k, and write down the result that you're trying to prove as if it were true for this value. Prove that if the result is true for n equals k, it must also consequently be true for the next value, n equals k plus 1. And it can help here to write down the target result, i.e. the result if it were true for n equals k, as this gives you something to aim for with your algebraic work. You must then explain that as you've shown the result is true for n equals k, it must then also be true for n equals k plus 1, and because the result is already true for n equals 1, by induction, it must be true for all values of n greater than or equal to 1, or whatever your starting value is. You must conclude your argument and write down the result and state that it has been proven. Now, in today's lesson, you are going to explore some proofs by induction involving recurrence relations. So just a reminder as to what a recurrence relation is, in case anyone has forgotten. It's sometimes also called an iteration formula. So, for instance, an iteration formula might be something like un plus 1 equals 2un plus 5. You're then given a starting value, u1, which might be equal to, let's say, 3, and you need to be given a starting term, otherwise you can't generate the next term. u2 would then equal 2 times u1 plus 5, so that would give you 11. u3 would then equal 2 times u2, which is 22, plus 5, which is 27, and so on and so forth, and you can generate the whole sequence. Now, the purposes of today's lesson is to look at proving what the nth term is using the information given in the recurrence relation. So have a look at the next 3 examples which illustrate this process. So in this recurrence relation that we're given, u1 is equal to 3, u2 is then equal to 3 multiplied by u1 take away 5, which comes to 4, and u3 is equal to 3 multiplied by u2 take away 5, which is 7. So a sequence is defined by this recurrence relation here, and we then have to prove that the nth term can be defined by this general formula here. So starting off, let's prove that the result is true for n equals 1. To give myself a bit more space, I'm going to do that up over here. So for n equals 1, first of all, we know that we're given u1 equals 3. Now, what does the red formula give us for u1? It tells us that that would be equal to 3 to the power of 1 minus 1 plus 5 all over 2, which of course gives us 1 plus 5 over 2, which is 6 over 2, which is 3. So it works. So the result is true for n equals 1. Must always make sure we include this check. So the next step is we're going to assume the result, the red result, is true for some integer n equal to k. So that then gives me uk is equal to 3 to the k minus 1 plus 5 all over 2. So now let's consider n equal to k plus 1. So we need to use the recurrence relation to find uk plus 1 and then prove that this gives us the same result as the nth term over here. So let's set up our target result. Do that over here. So my target result for n equals k plus 1, I simply take my general formula in red, uk plus 1, and let's replace n by k plus 1, which will give us 3 to the k plus 5 all over 2. Quite a simple result that we're aiming for at the end of this. So let's go back here, and we're going to use our recurrence relation to find uk plus 1. which is equal to 3 lots of UK minus 5, which is 3 lots of our red result, 3 to the k minus 1 plus 5 all over 2 minus 5 there. So let's have a look at simplifying this. So this becomes 3 to the power of k, if you think of that as 3 to the 1, plus 15 over 2 minus 5. And then let's write everything over a common denominator. This becomes 3 to the k plus 15 minus 10 all over denominator of 2. And there's our result, 3 to the k plus 5 all over 2, the target result. Or the target expression. So we have proven that if the result is true for n equals k, it is also true for n equals k plus 1. And because the result is true for n equals 1, by induction, it must be true for all integers n greater than or equal to 1. So let's move on to our second example here. A sequence is defined, again, using a recurrence relation, and we have to calculate for part 1 the value of the third term. So let's look at part 1. So a1 is equal to 1. Now a2 is equal to, using this recurrence relation here, 3 lots of a1 plus 1. So that is equal to 6. And then we can work out a3, which is equal to 3 lots of a2 plus 1, which is equal to 3 multiplied by 7, or 21. So those are our 3 terms. So part 2, we have to prove this result by induction. So part 1 of this will be to prove that the result is true for n equals 1. So for n equals 1, we know that a1 is equal to 1. Now, what does this general formula here tell us about a1? It would tell us that a1 would be equal to 5 multiplied by 3 to the n minus 1, or 1 minus 1, which is 0. Take away 3, all over 2. And what does that come to? Well, 3 to the 0 is 1. So this gives me 5 take away 3, which is 2, divided by 2, which is 1. So the result is true for n equals 1. So we've proven the result for n equals 1. So now we're going to assume the result, by which I mean this, is true for some integer n equal to k. Now that then tells me that I would have ak equal to 5 multiplied by 3 to the power of k minus 1 minus 3 all over 2. So that is my assumed result. So now we need to consider the next term, n equals k plus 1. And our aim is to find ak plus 1 using the recurrence relation here. Now, as we've been doing, we're going to put in a little sidebar and think about the target expression. So for n equals k plus 1, we would be aiming for a target expression, ak plus 1, using the yellow highlighted nth term. We would be expecting 5 multiplied by 3 to the power of k plus 1 minus a 1 minus 3 all over 2. Now how does that simplify? It simplifies down to 5 times 3 to the power of k minus 3 all over 2. So that is our target result that we are indeed aiming for. And we've got to get there using the recurrence relation and our assumption. So ak plus 1 is equal to 3 multiplied by ak plus 1. So that's 3 multiplied by, now what do we have for ak? Well, it's over here. We have 5 times 3 to the k minus 1, take away 3, all over 2, and then of course there's a plus 1. in the bracket. And we have to simplify this and show that we get to that blue result, the target result over there. So here we go. I'm going to rewrite this as 3. 5 times 3 to the k minus 1 minus 3 plus 2, all over common denominator of 2. I am somewhat running out of space here, but let's keep going. So this 3 here can multiply by 3 to the k minus 1 to give us 3 to the k. So that gives us 5 times 3 to the k. And then, of course, we'll have minus 9 plus 6. Or we could just add together the minus 3 and the 2 to give us minus 1 and multiply by the 3 to give us a minus 3 over 2. And there we have the target result. So it simplifies to what we want. So we have proven that using the recurrence relation, if we assume that the result is true for some value n, which we call k, the result must also be true for the next term, the k plus 1th term, and by induction, the result must be true for all values of n because we proved it was true for n equals 1. So please don't forget to write your concluding statements at the end of this, in which you must refer to all the key points that we keep covering. So in today's lesson, we're going to have a look at proof by induction involving recurrence relations. Let's delve into this in a bit more detail. So a sequence is defined by this formula here. Now, this is a recurrence relation, sometimes called an iteration formula as well. It allows us to move from one term in a sequence to the next term and then generate the next term and so on. We are then being asked to prove by induction that this formula also holds. Now that's a formula that allows us to algebraically define the nth term, which allows us to calculate any term in a sequence. Now, before we begin, I think we need to explore how this sequence is actually generated using the recurrence relation first of all. We're given that u1 is equal to 8. Now u2 is equal to 3 times u1 plus 2n, and n in this context is the same n that you're using here, which means it's n equals 1, because of course we're now working out un plus 1. So this would be 2 multiplied by 1 plus 5. So that gives me 24 plus 7, or 31, as my second term. Now, what about my third term? This is equal to 3 multiplied by u2 plus 2 times 2, remember what we just did, plus 5. So that is equal to 102, and so on. So our sequence is of the format 8, 31, 102, ... and we have got to use induction to prove that this result here tells us the nth term. So, of course, the first thing we want to do is prove that the result is true for a starting term, which of course is n equals 1 here. So prove the result for n equals 1. Now, we're given the information in the question that tells us that u1 is equal to 8. But does this formula here give us the same information? Well, let's check. 4 multiplied by 3 to the 1, multiplied by 1, multiplied by 3, this gives us 8. So the result is true for n equals 1. And we've completed the foundation of our proof. Now, let's assume the result is true for some integer n, which is equal to k. So this then tells us if the result is true for some n equals k, this gives us uk, the kth term, using this red result. So 4, 3 to the k, minus 3. And we now have to prove the result is true for n equals k plus 1. Now, as always, useful to think about the target result in this case. So I'm just going to clear a little bit of space over here and use that to draw out my target expression and just check I know what I'm aiming for. So my target result, the target expression, would be in the red result if we replace n by k plus 1. We would get 4 brackets 3 to the k plus 1 minus k plus 1 minus 3, which will just simplify. 4 brackets 3 to the k plus 1, that doesn't really simplify, minus k minus 4. So that is what we are aiming for at the end of this. So let's do it. Let's work out uk plus 1. So using the recurrence relation, uk plus 1 is equal to 3 multiplied by uk plus 2k plus 5. Remember what we said about the n values on the right-hand side there. Go back and look at the example we did at the beginning here. Now, what can we do with this? Well, 3 multiplied by uk, well, uk we have a result for over here. So that's 4 brackets 3 to the k minus 3. And then we have the rest of this, which is plus 2k plus 5. Let's simplify. Now, you can spot straight away. Let's leave the red 4 alone. 3 to the 1 multiplied by 3 to the k gives me the 3 to the k plus 1 that I need. Minus 3k minus 9 plus 2k plus 5. And then we are pretty much there. So let's just tidy this up. So minus 2k minus 4. This is the target result. So we have completed our proof. We just need to make sure we finish by writing a statement of completion. So if the result is true for n equals k, it is also true for n equals k plus 1. And as the result is true for n equals 1 by induction, the result is true for all integers n greater than or equal to 1. And just remember, by the result, we mean this here.